stuff that's sodium carbonate. Is there a metal in that?
Yes.
Yes, there is. So what do I have to look at in this room? Periodic table, absolutely. So what is the charge of sodium? 1 plus. Yep. And then carbonate's a polyatomic CO3 with what charge? 2 negative. Very nice. So I crisscross those. I get Na2CO3. And that's a solution. So what should I put behind this? AQ, thank you. AQ, it's an aqueous solution. I am reacting that with calcium chloride. Is there metal in that? Yes, calcium is. And what is the charge of calcium? 2 plus, very nice. And what is the charge of chlorine? 1 minus. Crisscross those. I get CaCl2. Also in solution, so what should I put behind it? Aqueous, good. AQ. This is a double displacement reaction, so on your sheet of paper, try to figure out what my products would be. So my metal and my metal are going to switch places. Doesn't matter which one you end up putting first. I'm going to do the calcium carbonate first. So I have Ca is still a 2 plus, CO3 is still a 2 negative. So when I crisscross those, do I need parentheses at all? I just get CaCO3. And that is, reading through the bottom. Calcium carbonate is the precipitate. So what does precipitate mean? Solid, very nice. So I've got a solid. And then my leftover stuff is my sodium, which I said was a 1 plus, and my chlorine, 1 negative. Crisscross those. I get NaCl. And that is also aqueous, because we know if we put salt in water, it's going to dissolve. So it's aqueous. Now I need to balance it, so balance it on your sheet of paper, please. Which one gets a coefficient put out front? NaCl, yep, table salt. Well, show me with your fingers what number we would put. Excellent, 2 is correct. Now I'm balanced. So I've got the first part down. Whenever I have a reaction now, I need to make sure I have a balanced reaction. So that part's done. This will go into your lab report. Remember, you have to subscript anything that is subscripted. You'll put parentheses around all of your state symbols. Again, that subscripting is important. A lot of people are still struggling to get that done. So we're going to do a DCP and a CE with this report. It's our last really big one for a while. So we need to think of the things that it's going to have us take data on in the lab. So raw data is important. Raw data. A lot of people have been not putting all of their raw data down. We want to make sure to get all of that raw data. Now it says in the procedure that we are going to mass about, or measure about 10 milliliters of 0.70 m. 0.70 m means that I have 0.70 moles over liters. That's the concentration of my sodium carbonate, Na2CO3. So that big M that it says in the lab, that's just moles over liters. So that means I have 0.70 moles of sodium carbonate dissolved in 1 liter of solution. That's really what it's telling me. I'm going to use that information later on. It says that I'm supposed to measure about 10 milliliters of it. So you're probably going to want to use your 25 or 50 milliliter graduated cylinder, depending on which one you have. You wouldn't want to use your 10 milliliter graduated cylinder, even though it's probably more precise. But if we're looking for 10 milliliters and you go slightly over, you're not going to get an accurate value. So I have my graduated cylinder and my liquid. Where do I measure from? The bottom of the meniscus. Yes, that lovely song that we heard, the bottom of the meniscus. Absolutely, we want to make sure that we measure from that. And we will write down our precise number. That's going to go in our data. It's going to be, let's say, 9.52. I know, it's near to 10. It says it should be near to 10. It's most likely not going to be exactly 10. But if it was exactly 10 and my graduated cylinder had this as my estimation spot, then I would have that as my value. If your graduated cylinder is more precise, and I got 10.00, that's my estimation spot. And we remember that our errors are plus or minus to that spot. So with this one, it would be 0.5 to my estimation spot. And this would be plus or minus 0.05 as my estimation spot. It's going to depend on the graduated cylinder that you have. If you have a really imprecise one, maybe it's just 10, plus or minus, probably not 5, it's probably going up by 1, so probably 1. If you've got one that's really imprecise, talk to me about it. We'll make sure we get the right value. Okay, what is missing on each of these numbers? Units. I need units on each of my numbers. So not only my value, milliliter, 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 but also on my errors. Milliliter, milliliter. God, so many of them here. I have to put units on every single one of them. And again, I'll write down my precise number. I'm not just going to write down 10, because I'm most likely not just going to have 10. And it's okay to not have exactly 10, or not exactly 10.00. You just have to make sure to write down what it is that you do get. Okay, so we've got that written down. I should also really have qualitative observations. Talk about whether it's colorless or if it has a color, like if it's slightly off-white or grayish. Write down if you can see particles floating around in it. Write down if it's clear, which means transparent, you can see through it. Good thing there's a rope on this. All of those things are going to be important qualitative observations for you to make about it. That's just the first step. First step is done. Let's look at the next step. I'm going to have more raw data to get for this. This time I have 0.50 moles over liters, and it's of calcium chloride, CaCl2. And I am going to need a precise value. I'm going to have my errors. I'm going to have units. And I don't want to forget qualitative observations. What does this stuff look like? And if you see in that step 2, we are adding this calcium chloride to the sodium carbonate, which means we're going to need more qualitative observations. What happens when you put them together? What do you see? What does it look like? Is there an odor? Is there a sound? Like, is it bubbling or anything like that? And you can hear a sound popping. You can feel the outside of the beaker to feel if it's like room temperature or if it's getting hotter or colder, so endothermic or exothermic. These are all things you should be writing qualitative observations about. Then, we're going to need more raw data. In step 3, it says allow the contents of the beaker to sit undisturbed for 5 minutes, and while you are doing that, you are massing a piece of filter paper. So you will determine the mass precisely. And that's easier for us since we've got the electronic balances. We will write exactly the number that it gives us, and it will depend on which one you're looking at. It's either going to be a number like that, or it's going to be a number like that. And then I would have my units, grams on both of them. And plus or minus, my error is going to depend on which of these I use. And it's one further out, so it's 0.05 grams, because I don't want to forget those units, or 0.005 grams. Since this is raw data, it's nothing being calculated. It's just the absolute error that I have from that machine, which is one of these two, depending on which machine I have. Then we will filter. I'm going to filter it through the funnel paper. Have we folded funnel paper in here before? Not in this one? Okay. There is a wonderful video on our class website that shows you how to do it. You fold it in half, then fold it in half again, then fold it in half one more time, and then open it up, and one little flap is going to fold down. You're going to put it into your funnel, and you're going to wet the sides of the funnel with some distilled water so that it stays stuck, because you don't want any spaces for the solid that we have, our precipitate, to go down through it into your beaker that's below. And you can watch the video on that if you would like. You also want to make sure to not overfill. So some of you are going to be tempted to pour out the entire beaker all at once and let that start going through. If you do that, though, you're going to go above where the filter paper is, and most likely then some of it's going to get lost into the bottom beaker, and you have to start all over again. So you have to filter twice or 3 times or 4 times. So you have to be careful making sure that it just goes onto the filter paper, not above and not in any empty spots in between. And then it says rinse the beaker with water from a wash bottle. We've talked about it a little bit, but it's still, even my 3rd semester kids struggle with this. When we have a wash bottle like the ones that are right over there, some people are tempted to like push it over, hold it like this, and then squeeze into whatever they're squeezing into, which for our case is a beaker. We don't want it in an angle like this because it's probably going to start leaking from here where it's tightened. So you always keep it upright, and then whatever you're holding gets put at the angle, and you squirt it in. Okay, so always try to keep the water bottle upright, and then you shouldn't run into any crazy issues of water spillage all over. And that's just to make sure that you get all of the precipitate out. So you can be making qualitative observations at this time too about how fine the powder is, or if it's really chunky, nice big chunks. What color is it? What does it look like as it's going through? If you do make a mistake and it goes above the filter paper and into the beaker and you have to refilter it, write that down in your observations. Okay, if there's something that deviates from this procedure that you end up having to do, write it down. Then you get to rinse the precipitate that's on the filter paper with water from the wash bottle. So you'll still have it above the beaker. So we've got beaker, filter, paper, and funnel. So there's my paper in there. It's going to go down, drippy, drippy, drippy. This part has to get washed out with the wash bottle as well. We want to make sure to get it clean of other stuff. Then we get to remove the filter paper and unfold it, and again we should be writing down lots of observations as we're doing that, and place it on some paper towel to dry overnight. It can just go into your drawer at that point. And then the following day we'll mask the precipitate because we are going to be determining the percentage yield. And I want to run through the calculations just a little bit to make sure that we are going to be on the right track for doing that. So this is a little bit different than the stoichiometry we've done so far because we don't have the mass of anything. What we do have is the volume that we use and the concentration of that. And if you look, let's say, we'll look at the first one, the sodium carbonate. We have 10, let's say 0.0, depending on which graduated cylinder I have and all of that, milliliters. And I have 0.70 moles over liters. Is there a way I could get to moles just with these two numbers? Yes, I see head shaking. Yes, absolutely I can, because all I have to do is convert milliliters to liters. So first step is going to be to convert the milliliters. Again, it's of what you actually use. So this is fake data for us right now. You're going to have to write down what you actually use. We're going to convert milliliters to liters. And I can do that because I know that there are 1,000 milliliters in every 1 liter. So I would start it out 10.0 milliliters times 1 liter over 1,000 milliliters. That's going to allow me to cancel out my units of milliliters. That's going to leave me just with liters of the calcium carbonate. And then I can multiply it by my other given, my 0.70 moles over liters. 0.70 moles per 1 liter. And what cancels out this time are my liter units. Now I just have moles. Now I can do the rest of the stoichiometry I would normally do. Again, this is fake data for us because this isn't necessarily what you're going to be starting with. But what do we get as our value of moles of calcium carbonate? 0.007. Now, I've seen in a lot of lab reports, I want to address this while lots of you are listening to me, seen lots of lab reports that if it is point something, people are not putting the 0 out front, which sometimes it's hard to see those points in your labs, which makes it look confusing. So make sure to put the 0 before the decimal point anytime you start out with a 0. Don't just leave it at 0.007. Do 0.007. And that's moles of the calcium carbonate. Oh, nope, sodium carbonate. Excuse me. Na2CO3. Hannah. Excellent question. We do it based off of the first value that we have, which again is going to be different depending on the data that you have. So really, I should have how many more zeros behind this to have the correct number of sig figs? Yep, 2 more. So my number with the correct number of sig figs is 0.00700 moles of Na2CO3. And we can talk about calculating the error for this later on. It's associated with the ones that we did with the constant in the last lab, so you can look back at that equation from the last lab to figure out what we would do with this one, but we can talk about that later as well. So this would be my starting point. Yeah, Grace?
Where did the 2 n zeros come from?
Because I have 3 sig figs here. These are all counting numbers, all the ones in here. So I have 3 sig figs in this, which means I have to have 3 sig figs at 700 in my last one. Not us yet. We go till 12:40 today. Okay. Now I can do the rest of my stoichiometry with this. So I have to start out with 0.00700 moles of Na2CO3. And I want to know, well, I'm going to have to figure out my limiting, but then I also want to know my percent yield. So I need to figure out my grams of calcium carbonate. So I'm going moles of one thing to grams of another thing. So let's do moles of 1 to grams of 2, which means I am going to have a 2-step. Anytime I have moles of one thing to grams of another, I'm going to have a 2-step. So I can set it up. My first step is going to be to get rid of sodium carbonate to get to the compound that I want, the calcium carbonate. So what thing that we've done already do I have to look at to be able to do that? Yep, look at my balanced equation, absolutely. So how many moles were in my balanced equation for sodium carbonate? 1 mole, yep. So that goes on the bottom. 1 mole of sodium, Na2CO3, goes on the bottom. And I'm looking to get to calcium carbonate. So what was my number of moles from my balanced equation of calcium carbonate? 1 as well, good. So 1 mole of CaCO3. So I can look at what I cancel out. I have successfully gotten rid of moles of sodium carbonate, and I am now 2 moles of calcium carbonate. So this is where I get to my second step, and I have to go from moles to grams, both of calcium carbonate. So where am I going to get some information? Yes, thank you, pointing at the periodic table. I need to figure out the molar mass of calcium carbonate, CaCO3. And on the bottom, what would I have? 1 mole of CaCO3. That way I can cancel out those moles of CaCO3. And then on the top, I would put my molar mass, grams of CaCO3. And then I'll be able to multiply through everything, divide by everything, and I'll get my theoretical yield based on the sodium carbonate. Then I have to also figure out the theoretical yield based off of my other reactant, which is the calcium chloride, CaCl2. Once I know both of those, I can figure out which one is limiting. So is it the Na2CO3 or is it the CaCl2? And then whichever one was limiting, I'll pick that as my theoretical yield. And from there, I can figure out my percentage yield, which is what you actually get on that second day of the lab, divided by what you are going to theoretically get based off of which one was limiting. and then we multiply that by 100%. And again, I would have gone through and I would have included all of my errors throughout. I've gotten my final error values. Yeah, Hannah.
So we don't have to deal with the like salt flow, the NaCl.
Correct. That's just an excess product. It's still going to be dissolved in the water, so it's going to be in our base beaker, which is a nice thing about this lab. Any of your products that you get, that you're not the solid one, any of the liquid products can just go down the drain with lots of water. It's just table salt and water. So that can just go down the drain. We don't have special waste for that. When we get to the precipitate part of it, we'll talk about that on our second day of the lab on Tuesday. Okay. What I would love is for you to have a sheet that you can take into the lab with you on Monday that has spaces for all of your observations and all of the things that you're going to need to put into your report. You can start thinking about some of the errors and how you're going to calculate those errors as you go through. If you would like, I'll be right with you. If you would like to get into the lab to be able to look at the graduated cylinders that you have so you can figure out the errors of those right away, you can do that as well. And if you were gone yesterday, you can also work on the stoichiometry sheet that's up here. And I'm going to put those answers up on the screen so you can check your work if you were here and if you weren't and you're working on it. Alec had his hand raised first. Yes, I would love to. Yeah.
This is only one trial.
Yeah, we'll only get through one trial of it. Yeah, we don't want to spend too much time on it. Yep, so that's going to be one thing in our conclusion and evaluation to discuss, talking about how we could reduce random